In this video, we're going to discuss the basics of chemical bonds, like what a bond is, how bonds form, or the basics of how bonds form at least. And we're going to discuss two types of bonds, although there are a few more. We're going to discuss ionic and covalent bonds. Now, okay. Some key terms that we need to be on the lookout for during the lesson are up here on the screen: bond, bond energy, ionic bonding, ionic compound, covalent bonding, polar covalent bond, electronegativity, and dipole moment. Okay, these are some words that are going to crop up a lot in this lesson and in future lessons. So we need to be aware of what they mean. Now, here on the screen I have three different versions of the same compound. Each of these show water, or H2O. So we have hydrogen bonded to oxygen, and basically this gives us an idea that a bond is nothing more than an attraction between two substances. So let me change the color of my pen here real quick. There we go. This right here is a bond, and it is an attractive force. Okay? You cannot have a jar full of bonds because it is a force, it's energy, not a thing. Okay? This is a bond. And while it is difficult to see, this overlap here is a bond. Okay? It is an attractive force holding two atoms together, or two ions. Now these are different ways to show them. This is called a Lewis dot structure, or a Lewis structure. This is called a ball and stick. And this last one is called a space film model. But they all show the same thing. They all show one oxygen bonded to two hydrogens. Now, one thing we need to talk about is bond energy. If I want to break this bond, if I want to get rid of it, energy has to go in. Energy. There we go. For some reason I forgot how to spell that. Energy goes into the bond in order to break it. That is called bond energy. That's how we know bonds are an attractive force and not an actual thing, because we're overcoming that attraction when we break chemical bonds. At the same time, when we form chemical bonds, we're actually releasing energy. Okay? Now, the first type of bond that we're going to discuss are ionic bonds. Ionic bonds form from ion-ion attractions. Oh, what happened there? Attraction. Okay, so ionic bonds form from ion-ion attraction. So we have this negative thing attracted to this positive thing, and that's how they stay together. Okay? And ionic bonds usually have a crystal lattice or a crystal structure. We're going to go ahead and say crystal structure for now. And what that means is they have a repeating pattern, like chlorine, sodium, sodium, chlorine. Okay, over and over again. And we notice this pattern is the same this way as it is this way, etc. Now, another characteristics of ionic bonds is most dissolve in water. There are some exceptions that we'll talk about later, but for all intents and purposes right now we can say that ionic compounds tend to dissolve in water, and we'll talk about that a little later in this video, why they tend to dissolve in water. And what that means is that the ions actually separate from one another and are free floating. Okay? So ionic bonds are also very strong attractions. Strong attractions. They're the strongest attraction. Okay? Now, the way ionic bonds form is a metal gives an electron to a non-metal. Okay? We notice that it follows this arrow to form a metal. These are neutral at first, and then they become charged after the electron trades places. Once they're charged, we have a positive and a negative, and they actually attract each other. Okay? So this process, called oxidation and reduction, actually creates ions that are attracted to each other. And typically, the metal will lose electrons. So the metal will lose, the non-metal will gain the electron. This is not always true, but for our purposes in this class, we can say that it's true. Okay? Which brings us to the idea of what is the other type of bond, the covalent bond. So, if you recall from our electron configuration discussion, the atom is roughly circular. Okay, and because the electron completely moves around the atom. And when the atoms are far apart, they don't really interact with each other. However, as we push them together, their electron clouds actually begin to overlap. Okay? And that is the attraction between them. What's happening is the nucleus of one atom is actually attracting the electrons of another atom. And so you get this kind of tug of war, okay, between the two nuclei. This is called a covalent bond. Covalent bonds share electrons, okay, in sort of this tug of war. And that's because when they share, the non-metal atoms become stable. This typically occurs between non-metals. Well, they become more stable. Let's say more stable, because some of them are not very stable, but they're more stable than they were before they bonded. Now, it usually occurs between nonmetals. These are covalent bonds, and they are weaker than ionic bonds. Now, what that means is that it's easier to overcome the attraction between the nonmetal atoms than it is between the ions. Okay, so this idea of overlapping electron clouds and sharing electrons is what makes a covalent bond unique. It's what makes a covalent bond special, and it's the thing we need to remember about covalent bonds. Now, there are two types of covalent bonds that we're going to discuss. We're going to discuss nonpolar and polar. Notice this little hydrogen and this bigger chlorine are not sharing equally. Okay? Instead, let me write that down. Unequal sharing. Since they are sharing unequally, what happens is most of the electrons are spending their time over here by fluorine. Okay? Rather than over by hydrogen. So they get what's called a partial charge. We show that the electrons are spending most of their time over by fluorine with this little lowercase delta right here. This lowercase delta with a negative, and that stands for partial charge or partial negative charge. What that means is that the fluorine is more negative than the hydrogen. And I'm just going to write more negative than the hydrogen. Okay, because the electrons are spending more time over there. Okay. So this unequal sharing creates what is called a polar covalent bond. And we call it a polar bond because we have a positive side and a negative side, a partial positive and partial negative. So we essentially have like a battery, like it's kind of like a battery where there's a positive end and a negative end, okay? Now, this is based on a property called electronegativity, okay? And electronegativity follows a couple of things. First off, we need to describe what electronegativity is. Electronegativity is the ability of an atom to attract shared electrons. Okay, so in the previous slide, if we were to go back, fluorine is more electronegative than hydrogen because it has a greater ability to attract electrons. So the electrons are spending more time with fluorine than they are with hydrogen, which gives it a partial negative charge. Okay, now we're not going to get into the details of having to memorize electronegativity. It's enough for us to remember these two rules when we look at the periodic table. Remember, there are patterns on the periodic table that we call trends. The first one is that it increases going from left to right. So it goes from smaller to larger, okay, as we go across the periodic table. And it decreases going down. So down a group, we have smaller and larger. Okay. And as we can see here, there is sort of a pattern. Okay. Fluorine, this is honestly the way I remember it. Fluorine is the most electronegative. So the closer you get to fluorine, the more electronegative you are. Closer to fluorine means more electronegative. Electronegative, which I'm going to abbreviate EM. By the same token, or on the other side of the same coin, francium is the least electronegative. Okay, and we see this pattern. As I go up the column, they tend to get bigger. Lithium is bigger than sodium, which is bigger than potassium, and so on. As we go to the right, we notice they tend to get bigger as well. Boron is 2, carbon is 2.5. Nitrogen is 3, 3.54, etc. So there is one exception, and that's hydrogen. Hydrogen is like carbon. It's like boron and carbon. Okay, so if it were on the periodic table, it would be between boron and carbon. Or if we positioned it just based on its electronegativity, it would be between boron and carbon. Whereas it's normally right here on the periodic table, but they separated it for the purpose of showing that it looks different. But we do notice this pattern of increasing, and there are some exceptions where it suddenly decreases for reasons we're not going to go into. And if you want to, you can talk to me later and we'll figure that out. But another thing you may have noticed is that there are no noble gases here. Noble gases don't have electronegativity values because they don't share electrons typically. It is possible, but we generally don't consider it. We generally don't think about it too much in regular chem because it just, to make them bond, you have to do extra stuff. Okay. Now, the polarity of a bond, how polar it is, depends on the difference between electronegativity values of the atoms involved. Okay? When the electronegativity of the first atom is approximately the electronegativity of the second atom, we get a nonpolar bond. Okay? When the electronegativity of the first atom is less than the electronegativity of the second atom, you have a polar bond. And when the electronegativity of the first atom is much less than the electronegativity of the second atom, you have an ionic bond. There's no hard and fast rule for differences between electronegativities. Like, oh, if the difference in electronegativity is 2.1, it's automatically ionic. Okay, there's no hard and fast rule. It's more like we rank them in terms of this is more polar than that. This is less polar than this. Okay? So for now, it's enough to recognize, is it nonpolar or is it polar? Or is it ionic? So that's where we have to keep in mind these things. That electronegativity is approximately equal, is less than, is much less than. Okay? So keep those things in mind going forward, that the electronegativity difference is what determines if a bond is polar. Speaking of such, here's a nice little chart that could help you remember. Intermediate difference is usually between 0.6 and 2.1. Anything less than 0.6 would be considered 0. Anything greater, anything greater than 2.1 is considered large. So these are the difference in electronegativities. Okay? And those are just general rules. They're not hard and fast. I mean, if you have something that's 2.2, it would really depend on what atoms were involved. So we notice that the covalent character increases as the electronegativity difference decreases, and the ionic character increases as the electronegativity difference increases as well. So this is what I mean by we don't really say it's this or this. We say it's more or less than. Okay. Now, this brings us to the idea of what's called a dipole moment. Give me a second to check my notes here, make sure I haven't skipped anything. Okay. This is what is called a dipole moment. Okay. Which is a fairly advanced concept. A dipole moment is when a molecule is polar. Okay. This arrow right here shows us the direction the electrons are being pulled. And this little plus sign corresponds to the partial positive side. The arrow corresponds to the partial negative side. Okay? So, in this case, we have a single bond. Okay? Bonds can be polar. Molecules have dipoles. And this will make more sense in a second. Because each individual polar bond will combine to make an overall dipole. Okay, let's take a look at water. Water actually has two dipole or two polar bonds. Okay? Each hydrogen-oxygen bond is slightly polar. But the thing is, what happens is this is sort of like a vector in the respect that these two arrows combine to form a new direction. So the molecule has a dipole that looks like this rather than the other way around, or rather than two individual arrows. So a molecule has a single dipole that's a combination of all the polar bonds. So a dipole, let's write that down. A dipole is a combination of all polar bonds, of a molecule's polar bonds. Okay. So they come together to form they can come together to form a new direction, a new net dipole. If you remember from physics, vectors add to form a resultant or a net effect. And the reason this is important is because of ions. Now, water has a net dipole that looks like this. And when there's a positive ion nearby, what happens is all the positives all the negatives attract to the positive, meaning all the waters are going to be arranged like this, okay, into what's called a hydration sphere. Not that that term is going to pop up anywhere, but it's just a cool term, hydration sphere. Now the opposite is true for if there's a negative ion. In this case, the dipole is still pointing the same way, but now the positive end is attracted to the negative dipole, or to the negative ion, forming a hydration sphere that's just inside out. This shows up a lot in biological molecules because if you think back to the phospholipid bilayer in cells, you have those little circles, okay, that are hydrophilic. Let me use my finger. And what happens is they attract other hydrophobic, or etc. Okay? So this whole idea of the phospholipid bilayer is actually based on whether or not they are attracted to water, and this is grossly not to scale, okay, or whether they're repelled from water, okay, which has to do with which way the dipoles are going. So the net dipole affects the way molecules interact. Dipoles affect molecule interactions. And we'll talk more about this as later in the year. Interactions. I think I'm going to run out of room. Oh no. Yep. Interactions. Okay. So if you have any questions or comments, leave those below. You can also email me and we will handle it. And enjoy.